So we will slowly introduce the Perron's method. So we will develop the machinery now required for that. So what do you know that it is easy to construct in the Perron's method, easy to construct sub and super solutions. Easy to construct sub solutions and super solutions. I will tell you that. Sub solutions and super solutions. Okay, so that's the one thing. Okay, so you say again we will start with omega in Rn. So assume the bounded. So we do that one, bounded, and then your problem is minus Laplacian u equal to 0. So you don't even have to use this Laplace equal to 0 in omega, and u equal to g on d omega. So the given assumption is basically g is a continuous function on the boundary. That's what we are taking it. So this is the problem we want to construct. Okay, g is d omega given. Okay, so what we will be doing is that it will be maximum principle to get easy results. That so basic idea about some of the motivations about harmonic functions. If u is to use maximum principle, to get results like, we will do that, results like u less than or equal to v for u sub-harmonic v super-harmonic. We will see these things now. V super-harmonic and u less than or equal to v on d omega. That's what the whole idea. So if you have so there is basically an arrangement. So if you do this one, all your sub-harmonic functions u less than or equal to v on the boundary, you see, and you have your thing, then you will get u less than or equal to v. So you have all collection of sub-harmonic functions basically on one side, and your super-harmonic functions basically on the other side. So the idea, the first step to take the maximum of all the sub-harmonic functions and the minimum of all super-harmonic functions, and you expect that u equal to v to have that supremum and infimum essentially coinciding. So we will not do exactly the same thing. So the basic idea is to look for all sub-harmonic functions satisfying conditions something like u less than or equal to g, which is the boundary value, and then expect a maximizing thing will become a harmonic function. Not only a sub-harmonic function, it becomes a harmonic function satisfying the boundary conditions. So the first step in this thing, define in this direction, define sub and super-harmonic functions, for continuous function. You already know that via mean value theorem we can do it. What we are going to do it is defining via maximum principles now. Motivation via, we will motivate you how can you define these sub and super harmonic functions for continuous functions via, it will coincide with mean value definition. Okay, via super harmonic functions for continuous functions. That's what we are immediately going to do. Okay, continuous functions via maximum principle. This is what we are going to, because these are all some of the defining properties of harmonicity. Maximal, not maximal, maximum principle. So let me give you a motivating argument and then we will use it as a definition. Okay. Motivation. Suppose U is in C2 of omega twice continuous. It's a smooth function. We want to define for continuous function, but you start with that's what we will always do for smooth functions, but continuous up to thing B is sub-harmonic. Okay, that is classical way. Classical way, because it's smooth way. This means that Laplacian of U greater than or equal to 0 in omega. Because it's twice differentiable, you can do that one. Now, if V is harmonic in omega, suppose V is harmonic in omega, V also belongs to the same space, C2 of omega, intersection C of omega bar, is harmonic in omega, okay, and U less than or equal to V on the boundary. Okay, so U is a subharmonic function, classical way, and V is a subharmonic function U, and V is a harmonic function which satisfies this inequality. Okay, it satisfies this inequality. Then what can you tell about it by maximum principle? So that implies immediately, what about U minus V? U is subharmonic. You think if you take Laplacian of V equal to 0 because harmonic, this implies that is U minus V is subharmonic and U minus V is less than or equal to 0 on d omega. So the maximum principle immediately implies you apply maximum principle, because the maximum cannot be on the boundary, implies U minus V less than or equal to 0 in omega. That's what we have discussed, recalled the result, or U less than or equal to V in omega. So you get it. So you see, so if you have a subharmonic function and a harmonic function satisfying this inequality, immediately you have the. We use this definition, this as the defining property. We use this to define subharmonicity for continuous functions. Subharmonicity for continuous functions. Okay. So similarly for superharmonic function. So you have your definition, a function U belongs to C, of course up to omega bar, is said to be subharmonic. A new definition is the same as the earlier definition if there is smoothness. Said to be subharmonic if the following hold. Following condition holds. Condition holds. What is that? For any ball, so you are asking for any ball. For any ball, so you have a domain here, omega. You have it, take any ball. It's not a fixed ball. for any ball B, of course it should be compactly contained, should not coincide, a ball B thing contained in omega, and if V is a harmonic function in the normal way, smooth function, V is a harmonic function defined on V, defined in omega, such that U less than or equal to V on d omega implies, so basically you are demanding that maximum principle U less than or equal, maximum principle is basically satisfied, but we write it in this way, in omega. You see, so this is what if U is subharmonic in the classical way, you know this result is true, so you are demanding that result because you don't need now the differentiability of U to define these definitions. Okay, sorry, so there is one correction. V is a harmonic function defined on B. This should happen for every B inside. Okay, in B. So if you take another ball, you should satisfy, because on the boundary of ball you have this. In fact, you don't have to even assume the continuity up to the boundary. You don't need even that one, because you are working out inside the thing. That's more than enough. But eventually in all our problem you will have continuity up to the boundary. For this thing you don't need it. Similar definition for superharmonic. Similarly, if we say U is superharmonic, we say U is superharmonic if U belongs to C omega. So you see, that's why generalization. Superharmonic if minus U is subharmonic. Equivalently, the others inequality. So you can say U is subharmonic. And U belongs to, so you can even define harmonicity for a continuous function. U belongs to is said to be harmonic if both U and minus U are subharmonic. So you see, you are able to define harmonicity via continuous functions. For continuous functions will do. Okay. This definition actually is due to a freeze. This definition is due to a freeze and coincides the definition via you can also define via mean value property. So all definitions are coincides the definition via mean value property. So you see, so you can define harmonicity in various ways. Either use the mean value property or use the maximum principle, or if it is smooth, you have the usual definition of point-wise definition of harmonicity. Okay. All right. In fact, there are more generalizations. More generalizations are available. More generalizations for lower semi-continuous, lower or upper semi-continuous functions. Upper semi-continuous functions. Lower is used for subharmonic, for functions generalizations for lower semi-continuous definitions to define sub-harmonicity. For upper semi-continuous, you define super-harmonicity. It plays your two harmonic, define harmonicity. Okay, so you can define, and it's all useful. You can define these notions for much more general than the continuous function. So what, before finishing here today, the rest of the thing, we want to define few of the properties which are very, very important. So we start with some properties, and you just go and verify these properties. We will be using again and again. Okay, so the one of the property, you can check it as an exercise. The properties are all almost trivial. While explain, I will say that the one of the first property is, which I am going to explain, this immediate property. If U is connected, U is sub-harmonic in a connected bounded domain. Important property, and you have to remember you have to understand these properties to understand the proof of the Perron's method. Connected domain omega, then I already defined you. The definition is something like a strong maximum principle. Then U satisfies the strong maximum principle. U satisfies the, now it's a new definition. Okay, you already know that it is sub-harmonic. You have the definition. Even with this generalization, you have the definition, a strong maximum principle, the SMP, strong maximum principle, strong maximum principle. That is, what is that means? That is if U or V, you want it, if V is super harmonic, everything we are defining that way. If U is super harmonic, so we have defined the definition for harmonic functions, but the maximum principle you will get it for the super harmonic function, satisfying U less than or equal to V on d omega, then either U less than V in omega, that is interior, or U identically V in omega. This is the same thing what we are telling. It cannot have an interior maximum kind of thing. So if U is super-harmonic, you know that U minus V is sub-harmonic. So it says that U minus V is sub-harmonic, and that's all we need it actually. U minus V is sub-harmonic, and U minus V is less than or equal to 0. And 0 is on the boundary. Okay, so you can apply that immediately, say that U minus V has to be, by the definition, maximum principle, it cannot have an interior maximum. Exactly like that earlier we have done, it cannot have an interior maximum. It's a similar proof. If you want, you can project it. Cannot have, that's why either it will be U strictly less than V in omega, or U will be identically V in omega. Okay, so that's the first. Second property is more interesting, which we are going to use it immediately. All the properties are which we are going to define, will be using it here. Okay, that's the very thing. This is what is called a harmonic lifting. You have to understand this very well. Harmonic lifting. Okay. So you are given a subharmonic function. Suppose U is subharmonic. sub-harmonic, and you have your domain here, and you omega, and you have a ball here, B. So you can restrict your U to B, and then you can lift that part of U as a harmonic function using what is called the Poisson integral. So look at here, of course, sub-harmonic, and you consider a ball of radius, let a ball of radius BR strictly contained in omega. Okay. Then you define Gx to be the boundary values of U, because U is a continuous function. So if the boundary value exists, you can define Gx is equal to Ux for X is on the boundary of P. This is on the boundary of the P. So I am restricting my UG is here. You restrict here. And consider this is where I define my G. Okay, so I define my G like this. Okay, then use G to define a function U tilde, which you can do it, function U tilde in B, you see, via the Poisson integral. You know that. So the Poisson integral actually solves the Laplace equation. If you know the boundary integral, using the boundary values on any ball, that's Poisson integral, we have solved the problem. Laplacian U equal to 0 in any ball and U equal to G on the boundary. So using the only boundary values of U, you can define U inside, which will be your harmonic, which will be a harmonic function. What is that definition? Via Poisson integral as U tilde of X is equal to R square minus modulus of X square by n omega n R integral over the boundary of R U of Y. G is U here. This is your G. This is your G. Okay. Why? This is only boundary values I am using. This is nothing but your integral. If I define denote kxy U of y. So you have your U of y, d sigma of y. This is over the boundary of the ball. So this is your U tilde of x. For all x in BR inside. So you see, so you have this defined U. Okay, and so you are defined U tilde here. So you defined U. U is defined everywhere. U is defined everywhere in omega, but U tilde is defined only inside, and U tilde coincide with U on the boundary. Okay, and of course, by definition, of course, then U tilde solves. This is what we have recalled the result, in fact studied in PDE1. U tilde solves minus of U tilde equal to 0 in BR, and U tilde of y is equal to U of G of y. This is equal to U of y or x. Let me use x only. X equal to U. This is in BR. U tilde of x. This is for all x in boundary of this ball. So that's what you have. So you have a harmonic function. So using the value of that U on the boundary, you can have your U tilde, and so thus U tilde is harmonic. Okay, so that's why U tilde is harmonic in BR. Okay, so with that we define now the harmonic lifting, define the harmonic lifting capital U in omega as, so you can do that one immediately. And what is the thing you want to define? U of x equal to U tilde of x if x is in BR, ball of radius R, and same U of x, it's a continuous function because on the boundary of BR you have the same value if x is in omega minus BR. Then this you can small thing, but you can prove it. Then U is, of course, you keep your sub-harmonicity. Okay, only at the boundary you have to verify that it is indeed sub-harmonic. So that's trivial because you have your U tilde is harmonic. So U is sub-harmonic. So the sub-harmonicity is not lost by defining this. Sub-harmonic in omega, and U is harmonic in the ball. Harmonic in BR, and it's the same value outside the ball. So whenever your harmonic function is given, you can take any ball you like it. On that ball, you can change that function U to make it a harmonic function by redefining it without changing outside and without losing the total sub-harmonicity. And that's what is called the harmonic, that's what we call it, the harmonic lifting. That one more property which I want to define, which will be using it here, is what is called the another property, the maximizing property of harmonicity. So let U1, this is also, all these are small things which you can actually prove it, be sub-harmonic in omega, then maximum, you can define the maximum of Ui, you call it Ux equal to maximum of Ux, I of Ui of x is sub-harmonic. So you see the maximizer preserves the sub-harmonicity, and minimizer for super-harmonic functions, minimum of Ui of x is super-harmonic. You see, and harmonic functions, both maximizing and minimizing functions. So the other things need not be true. You can find example harmonic functions. The maximum of minimum of sub-harmonic functions need not be sub-harmonic. Find examples. So this is an exercise, you can think of it. Exercise. Find examples to show minimum Ui of x need not be a sub-harmonic function. So need not be a harmonic function for Ui sub-harmonic. Okay. Similarly for super. So subharmonic functions by minimizing, so it's not immediate. Okay. So minimizer of subharmonic functions need not, minimizing function need not be a subharmonic functions for subharmonic thing. Similarly, maximum of superharmonic functions need not be a superharmonic functions. So we will more or less stop here this lecture. So let me set the stage for this thing. So to prove this, now what you want to prove is the Perron's method. Now we are in the setup of Perron's method, which we will start next week, next class. Perron's method, solvability of Laplacian u equal to 0 in omega and u equal to g. As I said, we need regularity of the boundary. Need regularity of the boundary. Of the boundary. So what we are going to define is class a concept of subfunction. Concept of a subfunction. Okay. So what we are going to do is that so you are going to, so probably I may give the definition of the subfunction and maybe recall again. So let me start with the definition so I can start immediately something more next class. Definition, subfunction. Okay, and we will do more things later. Let G belongs to C of omega. Okay, C of boundary of omega. C of, this is always on the boundary of omega, is a continuous functions, and we say we defined on omega, defined in omega, we say we defined in omega a subfunction if it satisfies the following properties. 1, V is continuous, V belongs to a continuous function up to the boundary, and 2 is the thing, V is subharmonic in omega, subharmonic. So it's a continuous function, continuous subharmonic function in omega. And the third property is the additional property. It makes it otherwise it's a standard subharmonic function. So subharmonic itself we define for continuous function. So the one of two properties are basically the subharmonic function. Third one is V less than or equal to G on d omega. So the extra thing we have defined is a subfunction is a continuous subharmonic functions whose boundary values is bounded by G. So it's a subfunction. We say the relative to G. You have to write that. Relative to G. Okay. And we define as G the set of all subfunctions. Is the set of all functions. So what we will next class we will prove SG is a non-empty set. SG is a non-empty set. And eventually what we are going to state the theorem, by maximizing that you will get a harmonic function. So we are going to eventually define a function u of x, what is called the supremum and of v of x, where V is in SG is harmonic. Of course, showing that it will satisfy the boundary condition. So the proving that it is harmonic is a bit delicate proof. So we will do this. So in the next class, the main aim is to show that the maximizer over all sub-functions, you get the solution of your not yet boundary value problem. At least you get that it is a harmonic function. So we will stop here and then we will continue in the next class.